Hi, stat students. Let's move ourselves right into Chapter 10, Correlation and Regression. We're just going to get to the first couple of sections in this chapter, and this is some review, some new stuff. You've done some of this way back in probably 6th grade or something when we talk about scatter plots. So bear with me. It kind of is combining old information and putting it into this context. So just in general, another area of inferential statistics involves determining whether a relationship exists between two or more quantitative variables. We are going to investigate whether there's a linear relationship between variables. If so, what is the strength? Is it a weak negative relationship, something like that? What type of relationship exists? And what predictions can we make? So we're going to do some extrapolation. So for instance, is there a relationship between a person's blood pressure and his or her age? Or is there a relationship between the size of a house and its appraised value? Or is there a relationship between the amount of time a person spends taking a test and the grade they get? Those could all be relationships that we investigate. So section 10.1a is all about scatter plots and correlation. We're going to talk about this today and tomorrow. So data are collected as ordered pairs. We know a lot of this, right? We know independent variables. That's what we manipulate. That is the explanatory variable or the x value. So that goes across our x-axis if we were going to represent that graphically. We know the dependent variable is not manipulated in any way. If we're thinking of an observational study, we might, manipulate our independent and then see what happens for our dependent. So this is the response. And we know it as the y variable for us math people. Research decides on independent and dependent, what we're looking at, what kind of correlation we might be looking for. Usually the relationship is clear, sometimes it's arbitrary, sometimes it's nothing like what we thought. So let's talk about correlation. So correlation is a statistical method used to determine whether a linear relationship exists between two variables. We're going to look at this in a couple different ways. We're going to see it visually, and we're also going to look at it mathematically. So determining if there is a linear relationship between two variables. Regression is the method used to describe the nature of the relationship. So how are they related? Is it a positive relationship or a positive correlation? We can think of that mathematically with lines of regression. So our regression can be positive, negative, or it can be nonlinear. So we could have linear positive relationship, nonlinear relationship. We'll look at those in just a moment. So if we're being visual about this, we may go to a scatter plot. You probably did these way back in your early younger days. So scatter plot is a visual way to describe the relationship. It's a visual representation. We've been doing these for a lot of different things. This is the relationship between the independent on the x-axis and the dependent variable on the y-axis, even if the scales are not the same, and they're typically not, right? If we just think about graphing in general. Maybe time is across the x and scores are up the y-axis. So this is a graph of the ordered pairs. We're not going to connect the dots, we're just going to look at them. I've got some examples down here on the bottom of what these look like. The horizontal axis, or the x-axis, is our independent, and the vertical axis is our dependent variable. Just like it's always been, we're just putting it into context of stats. So I know these little examples down here are probably not in your notes, but this is what we're talking about. We can have a positive relationship. If I think about being able to put a line through there, I'm a little off, but that looks like it might be. So that positive is referring to the actual slope, and they do group nicely in a line. probably a pretty strong correlation. Negative linear, so maybe something like that. This curvilinear, we're not going to do anything with it, but I would say it's nonlinear, but it definitely has a curved shape. And then this last one is just dots all over the graph. There is no relationship that we can see. It would be very weak if we had anything because the dots are just all over. These two up here are pretty strong relationships because the lines come out pretty clearly looking like a line, either positive or negative. So I'm going to have you make your own scatter plots. It's not really that difficult. Step 1, draw and label your axes. Remember to label, please and thank you, because we do want to know what we're looking at. The amount of calories eaten and the, I don't know, whatever we might be trying to correlate. Oh, goodness. Sorry, technical difficulty. Plot each point on the graph. You don't have to be super technical. We just want to get them on there. And then step 3 is to determine the type of relationship, positive, negative, nonlinear, or none, if that exists for those variables. So we would say positive, negative. We could probably group together nonlinear and none, but nonlinear does, that curvilinear thing does have a relationship. So let's look at an example here. I'm going to try to speed it along. So construct a scatter plot for the data obtained in a study on the number of absences and the grades of 7 randomly selected students from a stats class. So do you think that there might be some kind of relationship between the number of absences a student has and what their final semester grade is? I might think that there is a relationship there. So if I'm going to draw myself, construct a scatter plot, first thing I'm going to draw and label my axes. So my independent variable, whoops, is the number of absences. It even tells you that it's X. The dependent variable right here is the Y, the final grade. And then we're going to get ourselves kind of a rough graph together. Notice this is just a grouping or a situation in which we're just labeling. It could be a student's name, it could be A's, we could number them, whatever, but that's not having any bearing. So let's see, number of absences go up to 15, so I might do 2, 4, oops, that should be a 14, 16. Final grades go from, 43 up to 90. So maybe I'll do the little skip a few thing here. I'll do 40, 50, 60. All right, so student A, we've got ourselves 6 absences and an 82. 2 absences, 86. Notice they're not going to go straight across like we're sometimes accustomed to. 15 absences and a 43. Wow. 9 and 74. Sorry for me taking so long. 12 and 58. 5 and 90. 8 and 78. My board's a little off, but we can get the idea. So as far as our graph looks here, do you see any kind of correlation? Is there a relationship between the number of absences and the final grade? Well, it definitely, to me, looks like we've got some kind of linear negative relationship. So I'm going to ask you to do some of that in the assignment. So it's just an old school practice on plotting points, basically. Nothing too fancy. Don't draw the line through there. I know I drew my line through there. Don't draw that. Oops. We're just looking for what that scatter plot looks like. We're going to talk about that line later. So you get the idea, right? We've got another example. I think we can probably skip that. So, but if I did this, school district 1 through whatever, I've got what that looks like. So what are your thoughts on this? If we're trying to make a relationship between the number of teachers in thousands and the pupils per teacher, I don't really see any kind of clear relationship based on that scatter plot. So we would say it was nonlinear or no relationship. All right, so now we're going to get into some more technical stuff. So population correlation coefficient. Here's a new letter for you. It is a little like P looking thing, and it's actually rho, another Greek letter that I'm sure you're going to be excited to learn. So rho is the population correlation coefficient. That is the correlation computed using all possible pairs of data values taken from a population. So we're going to get ourselves, that's kind of like the mu compared to x bar. So this is for population. I've been trying to say all year, anytime we have stuff about population, it's always a Greek letter. Mu is population mean. Sigma is population standard deviation. Rho is population correlation coefficient. Well, typically, we cannot get all the possible pairs of data values from a population. So we're going to go with the linear correlation coefficient, which is just a nice R. So rho and R. Our rho is to R as mu is to x bar. So rho is computed from our sample data. And yes, we will have ourselves a nice formula to compute that. This tells us something. It measures the strength and direction of a linear relationship. Strength and direction. So positive negative relationship or a weak positive relationship. So we're going to do an actual computation and we're going to see what it tells us. So we're technically using the Pearson product moment correlation coefficient, the PPMC. Don't know that. We're just going to know how to compute our R, or our linear correlation coefficient. R is from the sample, rho is from the population, the correlation coefficient. All right, so properties of this correlation coefficient. First of all, it's unitless. There is no label for this. It's just a number, and we just use that number. So you're not going to say it's, 0.67 or whatever square feet. It's just 0.67. The values of R will always be between -1 and +1, inclusive, which means it can go up to +1 or down to -1, but it will not be 1.01. It will not go higher than that. So basically, if I were mathematical, I would say this. R is somewhere in between -1 and +1, including those values. Number 3, if the values of x and y are interchanged, you still get the same R. So it doesn't matter which way you go them. If we're going to use lists in our TI-84, it doesn't technically matter what is list 1 and list 2, x then y then x. If you converted your x and y values, one or both or either, to a different scale, like feet to inches, something like that, your R value is still going to be exactly the same. It does not matter. And last but not least, the value of R is sensitive to outliers, and it can change dramatically if you have them. So that might be one of the things that we look for. Do we have an outlier? Maybe we need to find the Q1 and Q3 and figure that out. All right. So when I look at this little table right here, and I don't think you have this in your notes, but these examples down at the bottom. So strong linear relationship negative is at -1. So the closer you are to -1, the stronger the relationship, and it's a negative slope. Strong positive relationship, the closer you are to +1. Here's the thing, don't forget, the closer we are to 0, 0 is really no relationship at all. So 0.018 is probably not much of a positive relationship. So we start getting weaker. So this would be a weak negative. This would be a weak positive. And then we've got that no real relationship in there. So I've got a couple examples down here just so you can see what I'm talking about. So letter A, R is equal to 0.5. So halfway, right? So about right here, 0.5. So it's kind of a weak relationship. You can definitely see the positive tendency to it. It's got potential, but the dots are pretty scattered far and wide. Notice this positive one, 0.90, so we're a lot closer here. Notice how the dots are clustered closer together, definitely a positive look to it. And then here is our perfect, R equals 1.0. I mean, this looks like I could just pick up a ruler. It's a very strong linear relationship, positive direction. And then we've got the same thing with our negatives. So same values, same idea, except they're negatives. So here's a -0.5. We can see some potential, but look at how scattered these dots are. So pretty weak, but it would be a weak negative. This 0.9 negative is a lot stronger, and then of course our perfect -1.00. That's as low as it can go, and that's as strong a positive correlation as you can find. All right, so we've got ourselves our R value for our samples. Rho would come from our population. All right, so here's our formula. It's a mess. Hang in there. You got this. Rho is equal to a fraction. In the numerator, you've got n times your sum of xy minus your sum of x's times your sum of y's. In your denominator, you've got a giant radical, and then 2 bracket parentheses in here. So watch out for these guys. The first bracket parenthesis is n times the sum of your x squared values minus the sum of your x's squared. And then, kind of running parallel, the second bracket inside that denominator is n times the sum of your y squared values minus the sum of your y's squared. So this really tells me if I've got to know x, y, the sum of my x, y's, the sum of my x's, sum of my y's, sum of my y squares, all those, I'm going to need to make a table. So n, we all know, is the number of data pairs, or our sample size. We've got that. And then I felt like it was noteworthy over here. When you do calculate your R, round to 3 decimal places. 3 decimal places. So let's do just a quick step-by-step, and then we'll do an example. Here we go. So procedure for finding the value of the linear correlation coefficient R. So steps 1 and 2 kind of go together. So step 1, make a table. Step 2, we're going to fill out. Notice this is the table that you should probably have. You need to include your x values, your y values, those will be given, your product of your x times y, your x squares, and your y squares. At the bottom of this table, we're going to have to do some sums. So place all your values of x and y in each column. Place the product of x and y. Square each x value. Square each y value. And then at the bottom, don't forget to find the sum of each column. Once you've got all that, the hard part's over. You're just going to substitute those values into the formula. Hope that your calculator work is pretty good, and find your value of R. I brought that back over again just to make sure that you saw that every single part of that table, setting up your table in step 1, is a part of that formula. So honestly, at this point, it's harder calculator work than anything else. Just make sure you get your right numbers. So this kind of brings me back to the dependent samples when we did the finding the hypothesis test for dependent samples, and we had to do the differences and the sum of the differences, but there's not even a subtraction problem here to mess up a sign or something. So, all right. So let's do an example. I'm going to ask you to do this as well. So absences and final grades. So for the data in example 10.1 that we made the scatter plot for, compute R, or the linear correlation coefficient. We already have this data. We already noticed that it has a negative slope. We want to see how strong or weak it might be. So steps 1 and 2, we're going to put all of our data in this table. So I'm going to go back. Give me a minute. I'm going to just pause and add that. You pause as well and add that. All right, so I've got all my X and Y values in that table. So now I'm going to just start doing all the math. So I'm going to do 6 times 82 and put that product. I'm going to do X squared and stick a 36. I'm going to do 82 squared. I don't know what that is. But then don't forget, once we do all that, we need to find all of our sums. So the sum of X, I've got all these guys. Let me jot these down, is 57. I've got the sum of my Y's is 511. I know I didn't fill in all this information, but for the sake of time, I'm just going to jot down what my sums are. If you do the math and you get something different, please let me know. But I did the math once, and I don't want to bore you. This is actually the sum of X, Y. And this, 511, yeah, okay. All right. Sum of my X squares, I've got a 579. And the sum of my Y squares, I've got at 38,993. And don't forget, your N is 1, 2, 3, 4, 5, 6, 7. I've got 7 sets of ordered pairs. All right, so I know I skipped a lot of math, but this is math, right? You can go to your calculator. You can do X times Y. You can add all these values up. You can put these in your TI-84 and let it do the work for you, whatever makes you happiest. So step 3 then is getting everything into our formula. So let me go back. Thought I had that formula in here. Let me go back for just a moment and grab this formula. Maybe I can grab that formula. Uh-oh, here we go. Got scared for a second there. I'm going to grab this formula and paste it so that we can get all the stuff that we need. So when we go to calculate this correlation coefficient, I'm going to set myself up a fraction. So n is equal to 7 times my sum of my xy's, which I've got right up here. I can hardly see. 3745 minus the sum of my x's minus the sum of my y's. So far, so good. All right, so then my denominator, don't forget it's a giant square root. It's got 2 brackets within it. The first bracket is sample size times the sum of my x squares, 579, minus the sum of my x's squared. My second bracket is the same thing, just with the y's. So my sample size times the sum of my y squares, 38,993 minus the sum of my y's squared. This is where the calculator work might get a little bit messy, so use that fraction button to your advantage. Do what you've got to do there to figure out how to make that work. When you do the math, you should end up with a linear correlation coefficient of negative 0. Remember, 3 decimal places, 944. Again, you might take a minute to make sure you get the same calculation, but negative 0.944, that's a pretty strong linear relationship. Closer to negative 1 is a strong linear, so negative 9.944 is pretty strong. So I'm going to have you do a couple of those calculations, and you should be good to go. Again, the math's not hard, just lots of things to keep track of. Make a table. There is one more example. I think we'll skip this. Maybe we'll do this one in class just to make sure everybody's good. That is it for section 10.1a. Sorry to talk your ear off. Have a great day. I'll see you next time.